Keeper 5.8, polar area. All right, so our area formula for polars, we have the integral from alpha to beta of 1/2 r squared d theta. You just need to remember the formula or the setup for your polar area. All right, so for example 1, it says determine the area of the inner loop of r equals 2 plus 4 cosine theta. So the very first thing we're going to do is graph the function. Make sure, again, you notice the form of the function is a limit sign with a loop. On the positive x-axis, since it's positive cosine, we have a maximum distance from the pole is 6, and we have a loop length of 2, since 2 minus 4 is 2. And so I graph the function, and I see that my inner loop, that loop is what we're trying to find the area of, so I shaded that green. I also noticed that this thing starts at, the loop starts at 2 pi over 3, and it ends at 4 pi over 3. And I could really set that up by taking my R equation and setting equal to 0 to see where it touches the pole. All right, so now that I notice that the loop starts at 2 pi over 3 and ends at 4 pi over 3, I can find my area. So I have the integral from 2 pi over 3 to 4 pi over 3 of 1/2 of my function squared. All right, now working that out, I get the integral from 2 pi over 3 to 4 pi over 3 of 1/2 times, when I square it out, I get 4 plus 16 cosine theta plus 16 cosine squared theta. Working that out some more, using my power reducing formula, I get 2 plus 8 cosine theta plus 4, 1 plus cosine 2 theta. And then simplifying that a little bit more, I get 6 plus 8 cosine theta plus 4 cosine 2 theta. And now when I integrate, I get 6 theta plus 8 sine theta plus 2 sine 2 theta from 2 pi over 3 to 4 pi over 3. When I plug that in, when I plug in my bounds, I get 4 pi minus 6 root 3, which approximately equals 2.174. All right, so in example 2, it says determine the area that lies inside of r equals 3 plus 2 sine theta and outside of r equals 2. So again, the first thing I'm going to do is graph it and shade the region that I'm trying to calculate. Remember that r equals 3 plus 2 sine theta is a limit sign without a loop. It's on the positive y-axis with the maximum distance from the pole of 5. And r equals 2 is just a circle centered at the origin of radius 2. And so here's my graph. And since I want to be inside the limit sign but outside the circle, I'm shading in this green region that you see. All right, so now to determine the area, the first thing I need to notice is that I need to figure out where these things intersect, so I can figure out what I'm calculating the area from and to. And so to do that, you can simply set the two equations equal to each other, and you get sine theta equals negative 1/2, or sine equals 7 pi over 6, 11 pi over 6. All right, so now I want to find the area, and so to find that area, again, I'm going to integrate from negative 11 pi over 6 to 7 pi over 6 of 1/2 of my function squared. But notice now that I have like an outside function and inside function, so I'm going to do 1/2 of the outside function minus the inside function squared, almost like top minus bottom type situation. All right, so when I simplify that out, I get 1/2 times 5 plus 12 sine theta plus 4 sine squared theta d theta. Cleaning that up using power reducing, I get 1/2 times 7 plus 12 sine theta minus 2 cosine 2 theta. And then when I integrate that, I get 1/2 7 theta minus 12 cosine theta minus sine 2 theta. Now plugging in my bounds and simplifying, I get a final answer of 24.187. All right, so example 3, it says determine the area. So we have the same function, but we want outside of the limit sign and inside of the circle. And so again, we have to remember that these graphs intersect at 7 pi over 6 and 11 pi over 6. And so if I want outside of the limit sign but inside of the circle, as you can see in my graph, the green shaded region is what we're calculating. All right, so again, I'm doing the integral from 7 pi over 6 to 11 pi over 6 of 1/2 of my outside function, which is the circle squared, minus the inside function, which is my limicon squared. So once I clean that up and simplify, I get 1/2 of -7 minus 12 sine theta plus 2 cosine 2 theta. And then when I integrate that and plug in my bounds, I get that my integral, or my area, is approximately 2.196. All right, so example 4, it wants the area of the inside of both the limicon and the circle. And so again, you can see my shaded region is shaded in green. Now we have two methods of doing this. The first method would be to take the area of the limicon and subtract the area that we found in example 2. All right, so if we do that, we would have the area of the limicon is 1/2 times 3 plus 2 sine theta squared minus the area that we calculated in example 2, which was 24.187. When I calculate this out and simplify it, I get that I'm integrating from, or I found the integral from 1 to 2, or from 0 to 2 pi of 1/2 11 theta minus 12 cosine theta minus sine 2 theta, and then minus the area from example 2. So I get 11 pi minus 24.187, which is 10.370. Now method 2 would be just to work kind of straight up and not use anything from a previous example. So I would take the area of the circle, and I guess we technically are using the area from example 3, which would be the outside top piece or the bottom piece of this little red circle. So the area of the circle, again, and this was what I meant by not really using anything else, the area of the circle, we could just use the area formula, which is pi r squared. Since the radius of the circle is 2, we do pi times 2 squared minus the area that we already calculated of 2.196. So when I calculate that out using my calculator, I get 10.370, which was the same answer that I got in method 1. Both methods are valid. It's just kind of how you see the picture to calculate that area out.